Good morning to everyone. I'm Dr. Sumi MS. The topic of my today's presentation is spectroscopic techniques from Unit 4 Nanostructures and Characterization Techniques. On completion, the students will be able to explain the different types of spectroscopic techniques and their applications in nanotechnology. Spectroscopic techniques. The most commonly used spectroscopic techniques in nanotechnology are listed as UV vis spectroscopy, that is ultraviolet visible spectroscopy. So here the purpose is to measure absorption or transmission of UV and visible light, and in nanotech it is employed in analyzing size and concentration of nanoparticles like gold and silver, and also monitoring the band gap in semiconducting nanomaterials. Examples are surface plasmon resonance in gold nanoparticles. The next one is FTIR spectroscopy, that is Fourier transform infrared spectroscopy. It identifies chemical bonds and functional groups via IR absorption, and in nanotech it is employed as surface functionalization and ligand attachment on nanoparticles and characterization of carbon nanotubes, graphene, etc. Examples are it's employed in confirming the presence of carboxyl or amine groups on nanoparticle surfaces. Raman spectroscopy. The purpose of Raman spectroscopy is to provide information on molecular vibrations and crystal structures, and in nanotechs they are employed in studying carbon-based nanomaterials like graphenes, carbon nanotubes, and also in detecting strain defects and layer numbers in two-dimensional materials. Examples: identifying single layer versus multi-layer graphene. X-ray photoelectron spectroscopy. The purpose of this spectroscopy is to analyze surface elemental composition and chemical states, and in nanotech it is employed in surface chemistry and oxidation state analysis of nanoparticles, thin film analysis, and surface contamination detection. And its examples are determining oxidation level in metal oxide nanoparticles. X-ray diffraction. The purpose of X-ray diffraction is to determine crystalline structure, and in nanotech it is employed in identifying crystal base phases and sizes of nanoparticles, and also in structural analysis of quantum dots, nanowires, and nanotubes. Examples: measuring crystalline structure size using Schrodinger's equation. Photoluminescence spectroscopy. The purpose of this photoluminescence spectroscopy is to measure light emission after photoexcitation. In nanotech, it is employed in the band gap analysis of quantum dots and semiconductors, and also in detecting the defects or doping effects in nanomaterials. Examples include characterizing optical properties of cadmium selenide quantum dots. Electron energy loss spectroscopy. The purpose of this electron energy loss spectroscopy is to provide information on elemental composition and bonding. And in nanotech, it is employed in high resolution chemical analysis in transmission electron microscopy, and also in probing electronic structure in nanomaterials. Examples include studying oxidation states at the nanoscale. Surface enhanced Raman spectroscopy. The purpose of this spectroscopy is enhanced Raman signal using metallic structures, and in nanotech it is employed in ultra-sensitive detection of molecules such as biosensing, environment sensing monitoring, and examples include detecting trace levels of pollutants using silver nanoparticles. Energy dispersive X-ray spectroscopy. The purpose of this spectroscopy is to provide elemental composition via X-ray emission, and in nanotech it is combined with SEM or TEM type of spectroscopy for localized chemical analysis, and the examples include mapping elements in core shell nanoparticles. Nuclear magnetic resonance spectroscopy. NMR spectroscopy is a powerful technique that is used to study the structure, dynamics, and interactions of atoms and molecules. In nanotechnology, NMR is especially valuable for understanding the chemical environment, surface functionalization, and dynamics of nanomaterials at the atomic level. Application in nanotechnology. Understanding surface chemistry of nanostructures, molecular interactions on nanoparticle surfaces, drug delivery systems. Dynamic light scattering. Dynamic light scattering. Dynamic light scattering, also known as photon correlation spectroscopy or Quasi-elastic light scattering is a widely used technique in nanotechnology to measure the size distribution of particles in suspension, especially in the 1 to 1000 nanometer range. The purpose of this method is to measure the size distribution of nanoparticles in suspension, and it has applications as characterizing colloidal stability, particle sizing, nanomedicine, and drug delivery. Quiz questions on spectroscopic techniques. What are the most commonly used spectroscopic techniques in nanotechnology? Define electron energy loss spectroscopy. What do you mean by dynamic light scattering? Thank you.